So good morning. So let's continue with chapter 4 of Arnold. And we have already discussed that there are two versions of the linear model. One is the coordinate-free version of the linear model, wherein we assume that our yi's are normally distributed. Our y are n by 1 vectors with mean mu sub I. So each of the yi has its corresponding mean and it has a constant variance sigma squared. And we can always transform this into a coordinatized version wherein our mu will be equal to a matrix X, which is a basis matrix for your subspace V. And then beta will be a unique p by 1 vector such that your mu, which is equal to the expectation of y, will be equal to x beta. And beta here will be in terms of your basis matrix x prime x inverse x prime mu. So an equivalent version of the coordinate-free version for the linear model or of the linear model is the coordinatized version of the linear model, wherein mu here will be equal to x beta. So there are advantages and disadvantages of doing coordinate-free and coordinatized version, and these are the ways or the of defining your space and why coordinate-free version is usually more appealing when we try to prove or derive some estimates. So examples of linear models are the one sample model, wherein we just have a simple model wherein yi is just equal to theta sum plus some epsilon, no? So it is a one sample model. So we are saying that your yi is just equal to your mu, where mu here is a vector of thetas. Another is the one-way analysis of variance. In one-way analysis of variance, you know that what we are doing here is we are trying to see if different treatments will be different. So usually the data layout for one-way and one-way analysis of variance is something like this, no? Wherein you have observations here for balance. Ibig sabihin, all of them has equal NIs. And we are trying to compare if the theta here is different from the theta here and the theta here. So that's why you have your vectors or your mean there will be for all theta 1s for each of the corresponding yi's there. So equivalently, mauna siyang scenario. Mauna imong vector of theta. So theta 2 until in this case, k is equal to 3. That is theta. So what we are doing is we are trying to find out if the means are different among the different TIs or treatments. So for the coordinate-free version of the linear model, all you have to do is to define your k-dimensional subspace. We call that V2, and you assume that your mean vectors there or your parameters there are elements of your k-dimensional subspace. So that is your model there. So it's still like y is equal to a mean mu there, but your mean mu there is comprises of different thetas, to theta k, no? Plus some epsilon. for two-way analysis of variance with no interaction. So data layout usually looks like this. You have factor 1 here, where your factor can have some levels there. And then you have factor 2, and it has its corresponding level. So with no interaction, so pwede na siya na entries din or you can have replicates in each of the levels and factors. Pwede po single. So that's it. No? So kining mga yi1 to y1c diha is the number of entries here per 1. So 1, 1. So this is your 1, 1. No? So this is assuming that this is your 1c. No? This is assuming that you have only one entry inside. No? And so on and so forth. So this is YRC. So this is the number of rows and the number of columns here. And this is explained by this model. So in general, it's explained by this model. So your theta here is just your overall mean. Alpha I is talking about if there are row effects, no, among the rows na by effect, that is there differences among the rows, and beta j here is differences among the columns. So in general, your model is theta plus alpha I plus beta j plus some for each of them ij, no. So we are looking at that particular model. So in coordinate reversion, all you have to do is to establish your subspace, say V3, and the dimension of your V3 is the number of rows plus the number of columns minus 1. Minus 1 will be the after subtracting it with the number of constraints. So ang imong model gives will be number of number of rows plus number of columns plus 1. 1 here will take care of theta. So this is the number of rows, which is your different alphas, and this is the number of columns, which is the number of columns, beta, no? Plus 1 will be for the theta. Now, why is this R plus C minus 1? Because in ANOVA, usually you will have constraints set by, this is alpha I, set by these two. These constraints will make your estimators distinct or defined because you will see later in ANOVA how there are 3 parameters here, but then again, the design matrix will be linearly dependent. So to make your estimates estimable, or you can estimate it uniquely, you have to set some constraints on that. So originally, this is your dimension of your V3, but you have to subtract this by 2 by the constraints, the number of constraints. So that's why it will give you R plus C minus 1. No? The constraints is added because there will be linearly dependent variables. So to make it linearly independent, you subtract it by the number of constraints. So this is still your linear models for ANOVA. But the concentration of this course will be more on the regression models, no? So can be the simplest is the simple regression model, but in general, you have multiple regression model. So the usual notation for your model is something like this. Say beta null plus beta 1 x1 1 plus beta 2 x1 2 and so on and so forth. No, so this is taken care of by the summation of xij j from 1 to. So this is equivalent to your theta, an overall effect, no, or beta null. So dinhi, if you look at the dimension there, dapat mo add ka og +1 po to take care of the intercept or the beta null. So you will have something like this. So your y is from y1 to yn, and then you have your matrix there and your betas. So dinhi, nagsugod ra siya beta 1, but you can always add a beta null here. But your design matrix here will be added 1, no? Na 1. So kung gusto ka kini siya ang model manggod nimo is just kini. So if you expand this is just yi is equal to x I 1 beta 1 because from 1 to r and so on and so forth, no, from x I r beta r. That's why your design matrix here is just this excess. So kung mu is x beta, so kini times kini na matrix din beta 1 to beta r. So summations na siya, no? You do that for all rows. But if you want to include beta null here, then you just add a vector of 1 before, so that this will be taken care of. So this is usually the model kung coordinate free na x beta plus epsilon. This is coordinatized version, but if you have a coordinate free version, you just define your subspace V4 and the equivalent model is this. Ang importante lang din is where will you get your mean vector. So your mean vector will be taken from a p-dimensional subspace of Rn. So sa coordinate free. So if P is equal to R, then the model is just the coordinatized linear model. However, when P is less than R, then the model is still a linear model, but not the coordinatized version. The coordinatized version is when you define it in terms of your mu is x beta, no? Other examples of linear models include nested analysis of variance, Latin square, or analysis of covariance models. In this course, we will concentrate with the regression models. Because for what we are looking here is a full rank. No? We have a full rank matrix. ANOVA models or ANCOVA models usually the excess there is not of full rank. Because it's not a full rank, that's why we have to define some constraints in the model to make our estimates unique. No? So these are the assumptions of a linear model. So the listed assumptions are with decreasing order of importance. So importante, the mean of pinaka-importante is that the mean of yi is a linear function of x sub I. So linear, no, linearity. Okay, linear models man or linear regression models. So basta ingon tag regression, we are assuming of a linear relationship between y and x. Equivalently, when we say when we say yi is a linear function of the xi, if we do model diagnostic, when we do model diagnostic, after you fit a model, usually mag-diagnostic man mo, no? Mutan-aw mo sa residual, no? The residual is equivalent of saying the error term. So that's why when we try to check on the residual, dapat ang residual mo follow lang siya o horizontal line, no? So when we try to check the residual about 0, mo follow lang siya horizontal line. So if it follows a horizontal line, then it means that y is a linear function with respect to x. Sometimes sa inyong undergrad, na-discussan man mo ana na if the residual will follow a funnel type behavior there, then it means that the assumption of linearity of y to x is violated. So that is equivalent, no? So when we say the mean of y is a linear function of x, it's just the same as saying that the residual or the error term is not following any pattern, or it's just constant. And then the yi's are independent. This will also imply that the epsilon ij's are also independent. The variance of yi are constant, which also means that the variance of the error terms are also constant with mean 0 and variance sigma squared. And the distribution of y is normal, which will also mean that the epsilons are normal. So talking about y is the same as talking about the error term. So if you look at the model, y is equal to, say, x beta, which is your mu, plus epsilon. When we talk about the error term, which is equal to y minus x beta, which is hot, no? The estimates there, equivalent na sila sa ani ng mga assumptions. So that if that is equivalent, the assumptions on y's can be related with the assumptions of e. No? So if e here is the difference between y and mu, or you can write that as y minus x beta, and your e's there are normally distributed with mean 0 and variance sigma squared, then equivalent to these listed assumptions on the y will follow with the assumptions of the e. So this is equivalent to assumption the ei's are independent, assumption number 2, that the y's are independent. The expected value E is about 0. This is equivalent to assumption number 1, that the mean of the y's is a linear function of x. And then the variance of EI are constant is equivalent to saying that the variance of YI are constant. So this is equivalent to number 3. And the EIs are normally distributed, which also means that the YIs are normally distributed. Okay? So, interrelated ng follow ng kung ni-satisfy ang assumptions on Y, dapat pag model diagnostic nato sa residuals, mo-satisfy ni siya. So when we are able to check this and these assumptions are satisfied, then the assumptions about Y is also satisfied. Now let's discuss what is the meaning of the different assumptions. So the EIs are independent. This is a strong assumption, but one that is often met in applications. Situations in which this application is not met is when we make several observations on each individual that is considered as a repeated measures model and generalized repeated measures. So when you have a repeated measures model, then this assumption is usually violated. And when we have a time series data, this assumption is usually also violated. Can you still hear me?
Yes, ma'am.
Yes, ma'am.
Okay. So in some situation in which the EIs are not independent or they are dependent, it is possible to assume that the covariance matrix of E to follow sigma A squared instead of just sigma I, no? Or what you do is to replace I by a matrix A, no? So that you can describe the components of non-dependence in the variability of EIs. Okay, the next example assumption is that the expected value of EIs, or on the average, the EIs will go to a mean zero. So this assumption implies that the mean of Y is in your subspace V. So in a multiple regression model, this assumption is violated if we do not include enough explanatory variable Xij in the model. So in a one sample model, it is violated if we have both men and women in the sample and the mean for men is so much different from the mean for women. Okay, so in principle, this problem can be corrected by adding more variables in the model. So for example, you are to compare men and women, but say your variable is age. The mean for men is found to be at 20 and the mean for women is found to be at 60. So ibig sabihin, you are dealing with different age group, and then this assumption that the expectation of EI equal to zero will most likely be violated because in the first place, there is a problem on your mean age for the two groups. Ibig sabihin, variable kayo, kini mga batanon, kini mga of the older age group na. So ages varies. So na ay variability that can contribute with respect to age. So in doing analysis, it is very important that at the first stage, or how you select your respondents to be included in your analysis or in your study, is a very important consideration that you should do before doing any study. No, you have to look at the variables under consideration. And constancy of variance or homozygosity of Y's. So this assumption implies that all observations have the same variance. In the K-sample model, it implies that the variance is the same for all K-samples. Or in multiple regression model, it implies that the variance of an observation is not dependent on the Xi. This assumption is bothersome since it is very difficult to argue that the variances should be equal. If such assumption is not satisfied, one can use the generalized linear model where we assume the variance of E to be equal to some constant, non-constant K sub I and its variance. No? However, there are some tests which you can do to see. For example, sa K samples, you have the popular Levens test, wherein you try to test if the different treatments here will just have the same more or less the same variability. No, the Venn test, or in the multivariate test case, you can have the Bartlett's test, and there are many other test statistics to verify whether the constancy of variance is satisfied or the homogeneity of variances is satisfied. And lastly, that the EI are normally distributed. This is the least bothersome among the assumptions, because this normality assumption can easily be satisfied when our sample size is large. So, and there are many other procedures when this assumption is not satisfied. You have many models that can be used when we have non-normal errors in our model. So two other assumptions on linear model, from coordinate-free version to the coordinatized version of the linear model. So aside from mu being in V, additional assumption is that V is known, the subspace V is known, it must be non-random. Of course, the vector mu is unknown, but it's a non-random vector. So these two assumptions are somewhat easier to interpret for the coordinatized version of the linear model, wherein our mu here will be equal to x beta, where x is some basis matrix. So equivalently, when we say mu is known, then we are saying that the matrix X is known and it's a non-random matrix. And when we say that the vector mu is an unknown parameter in the coordinatized version of the linear model, we say that the vector beta is unknown and non-random vector. So an example of a model in which the matrix X has random component is the correlation model, which is discussed in chapter 16 of Arnold. In the multivariate case, this correlation model will have a statistical method known as the canonical correlation analysis. No? So for that model, it is shown that the optimal procedure for the linear model are also optimal for the correlation model, so that it is not too serious of an error to assume that the model is a linear model when actually a correlation model. So usually regression and correlation analysis go hand in hand, no? So when we do regression analysis, we also do correlation analysis to see the degree of relationship, or the linear relationship, degree of linear relationship between X and Y, because it is very absolute in the assumptions for regression analysis that Y should be linearly related with X. An example of a model in which beta has a random component is the random effects model, which is discussed in chapter 5 of Arnold. So this is another type of model where the x's there are random. For this model, it is shown that the optimal procedures for the linear model may not even be valid for random effects model, so that it can be rather severe, a rather severe mistake to assume that the model is linear when in fact it is a random effect model. So we should be very careful when we do regression analysis and make sure that the assumptions on Y or the assumptions on E are satisfied. So either you will not check this assumption at the start of the analysis, but then you have to check these assumptions after doing the analysis to be able to have a good or meaningful conclusion of your model. So if you proceed with the analysis without checking the assumptions on Y, you have to proceed with the model diagnostic or checking the assumptions on the E or in the residual or on the error term. Okay, so the usual trend is fit the model, assume, and then do model diagnostic to check. Okay, so that's it for chapter 4. Let me have chapter 5. Maybe I have not yet uploaded this in Mole chapter 5, but let me just discuss it. I will upload it later. So our target here is to have your exam 3 and then exam 2 on April 12, and then schedule for your exam 3. Exam 3 will cover chapters 4, 5, and 6. Then after that, you will have your series of reporting. Nag-start na mo, napa ba mo subjects sa batch 2? Do you have subject for batch 2?
Inference po.
Did you start already?
Not yet po.
When is the start of batch 2? Wala pa? Wala yung nag-ingon?
Wala pa.
Anyway, so as much as possible, I want to end early. Siyempre, mag-intersect na siya sa inyong batch 2 so that you can concentrate on your batch 2 subject. But I will finish until chapter 6, and then you will have your exam 3 and then your series of report. For the series of report, it will not be twice a week, but we will have a separate schedule for Tuesday, Friday so that we can finish early. Okay? Kung kanus mo bakante, kung gabi mo bakante, then gabi ita mag-reporting. Okay? Anyway, so we will schedule on that later. So can you see lecture notes number 5?
Yes, ma'am.
Okay, so let's have lecture notes number 5. So in lecture notes number 5, we will be talking about sufficient statistic, and then later an MVUE statistic. So mag-inference pa man mo karon, no?
Yes, ma'am.
Karon na siya. Inference pa man, no? So
Yes,
you will,
ma'am.
this is an intersection of inference. So along the way, let me just have an overview of a sufficient statistic and minimum variance and bias estimation. Anyway, but this is relating to the linear model. Okay, so the first part of chapter 5 is the statistic for linear models. So the general linear model is that we observe a y. N here means that it is an n by 1 vector, which is normally distributed with a mean vector mu and variance sigma squared I. So it means that it has a constant variance. Again, in the coordinate-free linear model, all you have to specify is a mean vector mu, which is in a subspace V. No? So if you have a particular subspace, in general, gamito na nato V, pero kung naamoy particular na subspace as what I have illustrated in the examples in the previous notes na ay mga vectors na p by 1 lang, na apoy vectors kay na apoy space na matrix siya or p-dimensional, so dapat i-identify to mao tong natoy V1, V2 dito sa earlier na notes. So in general, let's have a space V which satisfies this condition that space mu, vector mu is in the subspace V. Here, V here is a p-dimensional subspace of Rn. p-dimensional. So mahimo siyang p-dimensional because this mu here will later be dependent on your dimensions of, for example, katong mu nato sa coordinate free x beta man to, no? But beta here is p by 1. So dapat kining basis matrix is p by p para kini siya it will be a p by 1 which is an element of V na naa siya sa p-dimensional subspace. So subset lang siya. P is less than n because it is a subset of R to the n. Now, you will see later that your mu here, this is actually unknown, no? This is unknown. And it will be estimated by mu hat. So if you recall, if you have a vector y here, and you try to have a model, say y is equal to mu plus epsilon in the one sample model, to have an estimate of y or to get the expectation of y, this is actually equal to mu hat. So that is an expectation. Now, by how mu hat is defined, it tells you that you can analyze the y with respect to a subspace V by looking at its projection. So mu hat is actually the projection of y onto V. No, so kung unsay projection ani, kana ang projection, this will actually be your mu hat. And the variance, this variance here, which is usually unknown, will be estimated by mu hat, sigma hat square, will actually be a projection on B perp. So where is B perp? B perp is the orthogonal subspace with B, no? So naa siya dinhi. Kini siya na vector dinhi. And then divide it by n minus p, or kini na vector na naa dinhi sa B perp. This is actually your B perp, will be n minus p times the square norm projection of y onto B perp, no? So y onto B perp, square norm projection. So when we analyze the mean or the estimate, okay? So you have a mu, which is to be estimated by mu hat, and you have a sigma square, which is usually unknown, to be estimated by sigma hat square. In terms of projection, this mu hat here is actually just equal to the projection of your y onto V, and this sigma hat square here is actually the square norm projection of y onto B perp divided by n minus p. N here is the dimension of your whole subspace, and p here is the dimension of V wherein mu is there. Okay. Okay, so you know that the projection of y onto B perp can be written as y minus the projection of y onto B perp. Mo tong giingon nako na si y is just a sum of the projection and the rejection, di ba? Mo man to'y term na to. And then, of course, you can always write the projection of y onto B perp as the difference of y and the projection of y onto V. Okay, so you have a result there. So ganina na lemma anyway. And then what happens here, substitution of the projection of y onto V by mu hat, you have that. And then if you try to expand this one into y minus mu hat perp times y minus mu hat, and then expand that, what you will get is y prime y, and then minus mu prime mu. Y prime y is actually the square norm the square norm of y, and mu prime mu is actually mu hat square norm of mu. So when you expand this, the middle term will be equal to 0. Why do you think? Because you will have a middle term here, no? Middle term na y prime mu prime and kay mu prime y and y. Now, nganong ang middle term not 0? And the middle term can be expressed as kini siya may mo man ni siyang plus unta. Pero ang kining middle term ma-express ni siya as minus 2 mu prime mu and mu prime mu hat, no? Para may mo ng 2 minus 2 mu hat prime mu hat man isa ka plus mu hat prime mu hat, mahimo na siyang nahimo na siyang minus diha. So ibig sabihin kining y nimo dinhi can be expressed as mu hat in terms of projection. Ngano na siya? Because you can always write the projection onto v prime to be equal to pb, and the projection of squared is just pb, no? So you can always write that as minus 2 mu hat prime mu hat. Okay, you can discover that. Try to expand and try to get this quantity here. So kung imong tanawon mura ra siya the square norm ang y man minus the square norm ang mu hat, but the derivation of that is you have to express this and scrutinize the middle term, why it is equal to 2 mu hat mu hat mu prime and mu, para may mong plus mu hat prime, no? Ano yung nahimong minus. Okay? Okay. The last equality of sigma hat is by theorem. Okay, actually we have derived that by theorem 2.5d. So just look at the proof of theorem 2.5d. Why this one is equal to this one. Okay, so the first theorem in chapter 5 is the projection of y onto v, or mu hat and sigma hat square are independent, and the distribution of mu hat and n minus 1 sigma hat square is chi-square distributed central. So how do we prove first independence? Okay. So note that V and B perp are orthogonal, correct? So if they are orthogonal by theorem 3.1b, sama ng theorem 3.1b. Ang theorem 3.1b nag-ingon at 3.11. Ingon din na kung si V daw orthogonal sa W, this is theorem 3.11b. Si V orthogonal sa W, then ang projection sa Y onto V and the projection of Y onto W are independent. So we will use this since these two are orthogonal, then the projection of y onto v and the projection of y onto b perp will be independent, but mu hat is a function of the projection of y onto v, and b perp is a function of the projection of y onto b perp. So this is actually the projection, square norm projection of y onto b perp, which can be written in this manner. So this is actually b perp y prime and b perp y, which can be written as y prime, b perp y prime, b perp y, but this one is just can be written as b perp. Oh. B perp y and y prime, because in general it's equal to this. Okay, so this can be expressed as the projection of y onto b perp times projection, the projection of onto b perp, and then this is the prime will be just equal to the projection onto b perp, but the square of the projection onto b perp is just the projection of onto b perp. So since it is a function of projections onto b perp, then we say that mu hat and sigma hat square are also independent, being functions of two independent projections also. Do you have questions? So this part here just proves that mu hat and sigma hat square are independent. Next, we show the distribution of mu hat and the distribution of sigma hat. So if you are asked to show that mu hat and sigma hat are independent, you need not write all of this. The solution is just these two statements here. No? Okay, next. Let's look at the distribution of mu hat. Now, mu hat, a function of the projection of y onto b perp, and we have a previous result. So, ibig sabihin, kung mo gamit mo previous result, for example, mayroon ko, show that mu hat and sigma hat square are independent. You have to show first theorem 3.11b, no, in your proof before mo conclude ani. This is a short proof, but when you are asked in an exam to prove that, you have to show first theorem 3.11b. Do you understand? So you have to go first in the process of showing 3.11b. So with the assumption that mayroon mo, suppose V and B perp are orthogonal, then ipakita nini mo, how do you show that these are independent? It has something to do, unsay gigamit na concept aning 3.11 pag-prove. Iyahang covariance matrix, di ba?
Yes, ma'am.
Dapat mapakita nimo na ang off diagonal 0, di ba? So diha ka dapat mo agisa ay dayon ka mo conclude. Do you understand what I'm saying?
Yes, ma'am.
So, ayaw ko hatagi na based on the result na independent sila. Dapat pag exam, you have to show this first. Why are they independent? Okay? That is how you show it during exam. Not that it was shown. It was shown already. Nadili na pwede because I'm measuring how much you learned or what concept did you use to say that this one the projection of y onto v and the projection of y onto b PERT are independent. You have to pass through the concept na you have to show that the off diagonal of the covariance of PBY and the projection of y onto b PERT are 0. Okay?
Okay po.
Okay, ma'am.
Next, distribution of the mu hat. So, gigamit ang 3.11a. So, automatic siya, no? Because this is mu hat. But to show that, unless niingon lang ko what is the distribution, then pwede ra diretso ang answer, no? And then this is true because if you have a result also that katong if y is in v, di ba? If and only if the projection of y onto v is y. Na siya result. And then this second part here, so automatic na siya, may mo ni siyang mu, straightforward, pero dapat familiar mo anang theorem 3.11a. That is showing that the distribution of the projection of y onto v is also normally distributed with mean equal to the projection of mu onto v and variance sigma squared bp. And this part here is necessary para makuha ninyo ang degrees of freedom sa chi-squared. So, dimension of b perp is n minus the dimension of v, but the dimension of v is p-dimensional man siya, so n minus p. And then you use this result, 3.12, gikuha man ni nato unsay distribution sa ato ang square norm, no? The square norm of the projection of y onto b perp, which is chi-square, with this non-centrality parameter, but then since mu is in v, you have a result also kung naa sa v, then the projection of u onto b perp is 0. Kaya naman na siya sa iyahang orthogonal complement. So that this part here will be equal to 0, and then the distribution of your sigma hat square pre-multiplied by n minus p will be a central chi-square. Okay? So in general, pwede ninyo isulat as n minus p sigma hat square over sigma square is chi-square n minus p central. No? Pwede inani na forma. This form here is familiar. That is actually the test statistic when you are testing variance, no? The morning test statistic niya when you are testing variance. Itong null hypothesis bitaw na sigma square is equal to a specific value. This is the test statistic, but your sigma hat here is usually your sample S square. And then this one will be the claim value kung pila imong gina-claim, which is chi-square. Central chi-square. So, theorem 1.1 or equivalently theorem 5.1 in Arnold shows that sigma hat and mu hat, sigma hat square and mu hat are independent, and these are the distribution of your mu hat and sigma hat square. So one is normally distributed and the other one is central chi-square. So the distribution of mu hat is a singular normal distribution since the projection on V is an n by n matrix of rank P. Singular. So it means unsa ganitong inverse nag-exist, singular or non-singular?
Non-singular, ma'am.
Non-singular.
Unsa ang matrix na ang inverse nag-exist? The singular or the non-singular?
None, ma'am.
None po.
Kung non-singular, inverse always exists. Before deriving density for non-singular, unsa gani ang naay ano? Ang non-singular naay inverse or ang singular ang naay inverse?
Ang non-map, non-singular ang na
Non-singular.
Ang non-singular ang naay inverse. So kini
Yes,
siya
ma'am.
Dependent pa ni siya sa in general kay singular man siya. So non-positive definite. Okay. So next, sufficient statistic. How do you understand sufficiency in your undergrad? What is a sufficient statistic? So when we say jointly, two-parameter model ni siya. But what do you understand about a sufficient statistic? Anybody? Mga BS stat? The formal definition of a sufficient statistic is with respect to the conditional distribution, no, of that statistic. When the conditional distribution is independent of the parameter. So ibig sabihin kung naamoy probability density distribution ana na random variable and you get the conditional distribution of that. So conditioned on some parameter, say theta, and the result is independent of the parameter theta, then we say that it is sufficient. So ibig sabihin the information enough siya for the sample. Pwede ra ang samples kay ang conditional distribution niya on theta is independent of theta. Ibig sabihin ang final conditional distribution niya dili siya function of the parameter theta. So sufficient. No? That is the formal definition. Sufficient siya. So based lang sa random samples, enough. Anyway. So if we talk about a normal distribution, this is the probability density function. Okay, so this is raised to the n because originally gi-product na siya for each of the density function sa imuhang normal I from 1 to n. So we are assuming here that y are independently and identically distributed na normal distribution. So ang kada isa sa atong f of x kay ano ra man na siya? 1 over 2 pi raised to the 1/2, no? And then 1 over sigma. And then exponential of 1 minus 2 sigma squared y minus mu I squared, no? So kini sa univariate case. So kung imong i-product na siya for all, this square here will be a square norm na in terms of vector y minus mu prime and y minus mu. And then from what we solved in theorem 2.5a, Pythagorean, we can express this in this manner. That is just adding and subtracting mu hat, and then group the terms, and then apply the square norm. So naani siya yung mga middle term, no? Naman na, may mu hat plus mu hat minus mu prime, and then katong isa plus diha. And then the middle term again will go to 0 ang middle term, ang cross product, kaya ang nabilin din kinira man apart. So mura siya a plus b squared, a squared plus b squared, manakay plus middle terms 2ab, no? Pero ang middle terms will just be equal to 0 in this part. So that ang mabili na lang ang a square and then ang b square. But this part here, is actually your n minus p sigma hat square. Why? Because this is actually the projection of y onto b perp square norm. No? Because mu hat here is actually the projection of y onto v. So actually, by definition of sigma hat here, that is equal to n minus p sigma hat square. So you can express now, you can express y minus mu, kinina part hindi ni sa imo ang probability density function as a function of sigma hat square. So ang imohang parameter din ni is sigma hat square, and then a function of mu hat. So according to the factorization criterion in chapter 1, no? Factorization criterion, kung pwede daw nimo i-factor ang imohang density function as a function of x man times a function of x with respect to your parameters. With respect to your parameters there. And na atong parameters is sigma hat square and mu hat. Then these two are sufficient statistics. So that is by factorization criterion. So you will learn more about sufficient statistic when you do inference. But for now, the general thing to know here is that you can show that a statistic is sufficient if the formal definition, if the conditional distribution of y given your parameter theta is independent of theta, that is sufficient. But a simpler way of showing that is to use the factorization criterion by Lehmann. That is, if you can factor your density function into two components, one is just a function of x, and the other one, mo na ni ang function on x or on y, pero constant lang siya. And then the other term is a function of y in the parameter, which is this one, which can be shown in this manner. Exponential man ni class, exponential of this plus this. So e to the a plus b is actually e to the a times e to the b, no? So function siya of a and b, or a function of mu hat square and sigma hat square and mu hat. So by factorization criterion, since we can factor it into of this form, then we say that they are sufficient stat. Jointly means together, you know. So together mu hat square and mu hat. Another characteristic of mu hat and sigma hat is its being complete or a complete statistic. Complete statistic has to do, if you look at the proof of Arnold in Theorem 5.3, has to do something with the neighborhood of the values of mu hat and sigma hat. So we will just accept the concept that aside from being a sufficient statistic, it is a complete statistic. So if you are interested on knowing what is a complete sufficient statistic, you study the proof of Arnold in Theorem 5.3. And of course, you can learn more on this completeness in your inference class. So dili lang kay kumudil ana kay sa inference class ninyo dapat i-scrutinize na what is a sufficient and a complete. For now, in linear models, you know that mu hat and sigma hat square are complete sufficient statistics. Okay. Next, we study, emphasize now our study in the coordinatized version of the linear model. So, aside from mu hat and sigma hat being a complete sufficient statistic, so atong mu hat sa coordinate free kay is just the projection of y unto v. Ng atong sigma hat times n minus p is actually the square norm of the projection of y unto b perp. So in the coordinatized version of the linear model, our mu is x beta. So equivalently, our mu hat will be x beta hat. Okay. Now our x beta hat with our beta hat equal to x prime x inverse x prime mu hat. So this is the coordinatized version of the linear model. We observe y to be normally distributed with mean x beta, a variance sigma squared I. Our beta is a p-dimensional vector and sigma is positive. X is a known n by p matrix of rank p. So rank p, the minimum between n and p. So ikuha na to ang rank p, not necessarily orthonormal. So let V be a subspace spanned by the columns of X. Then X is a basis matrix. And then since X is of rank P, the dimension of our V, since X is a basis matrix, will be equal to P. So in the coordinatized version of the linear model, mu is X beta. So that Y will be normally distributed with mean X beta and sigma squared will be the coordinatized version of the linear model. So we define beta hat to be x prime x inverse x prime y. It can be verified using Theorem 2.4c that mu hat will be equal to x beta or the projection of y unto v. Mao man ni atong mu, no? Mu hat. So if we since the x is not necessarily orthonormal, so the general formula of your projection from chapter 2 will be x projection x prime x inverse x prime y. No? Mani ang itsura sa ato ang projection kung not necessarily orthonormal unless kung orthonormal siya, mo simplify ang x prime x na identity, no? X prime x identity na siya basta orthonormal, so that the projection of y onto v is just equal to x prime x y. Pero wala man ta nag-assume ana, basta basis matrix lang siya, and our beta hat is defined by this. So mo nang ang atong mu hat is x beta hat. Okay? Is x beta hat. And then it follows that kinina part din mo ni ato ang beta hat, but if you get the expectation of y, that is equal to mu hat. So you can have beta hat as x prime x inverse x prime mu hat. Now, beta hat and mu hat are invertible. So you can derive beta hat in terms of mu hat, and you can derive mu hat in terms of beta hat, no? So they are invertible. Also, your variance or n minus p times sigma hat square in terms of the coordinatized version of the linear model will be equal to this by substitution of mu hat, that is x beta hat. And then if you expand this is y minus x beta hat prime times y minus x beta hat. You will obtain y prime y and x beta hat prime minus x beta hat prime and x beta hat. So the middle term here again, the twice something will be minus 2 something, but the minus 2 something is actually x beta hat prime and x beta hat, then plus x beta hat times x prime x beta hat. Mao na may tabo, mao ning minus ra ni siya. Okay? And then if we rewrite this in this manner, y prime man kini siya, may muna siyang beta hat prime x prime man x beta hat, and then expound beta hat in terms of this. Ma-factor na to ang y outside. Are you with me?
Yes, ma'am.
Opo.
Oh, kining beta hat isulat na ninyo in terms ani. Man ma-factor na dahil ninyo ang y dinhi, ang isa y prime kay kini siya kay y prime y man eh. So that ang y prime y identity na lang man kini dayon mabilin. Okay? Do you understand?
Yes, ma'am.
Okay, so i-try na ninyo og expound para makabalo, no? Na masulat din siya ani. Okay? Do you have questions? So gamito ninyo din pag-expand ana. Okay, kini siya kay ano man y prime y. Kini siya x beta hat prime x beta hat, which is x beta prime x prime man x beta hat. Man kining beta hat nimo kay x prime x inverse x prime y na siya. Manaapo ka ani. Man nanang kay y din man prime man so naapo ni siya y prime. So mao na i-factor out sa gawas, no? Are you following?
Yes, ma'am.
Then Kini siya y prime y mao ni ang identity I. Okay? So I think you can follow through that. So that is, in other words, we can always express mu hat as x beta hat, and you can always express your sigma in terms of your basis matrix and your y, no? So this theorem is talking about the equivalent version of a complete sufficient statistic of a complete sufficient statistic. Ganina, ningon ta na mu hat and sigma hat square, no? So karon it's beta hat and sigma hat square as a complete sufficient statistic for a coordinatized version of the linear model, and it is also telling you the same thing as these were independent previously. Beta hat and sigma hat square are also independent, and it is telling you that the distribution of your beta hat will be normally distributed with mean beta hat and variance sigma hat sigma squared x prime x inverse. Okay, so if mahitabo ng atong basis matrix kay orthogonal, ang x prime x here will just be equal to identity, and inverse of that is just identity. So beta hat, as long as orthogonal lang atong x's, mahimo na lang siyang beta and sigma hat, no? Pero kung orthonormal basis ang ato ang x, kay pag orthonormal man gud ang x prime x is just equal to the identity. So in general, inani ang formula sa ato ang inani ang itsura sa atong variance. But if we are dealing with orthonormal basis, that will be simplified. And we see that the expectation of beta hat is equal to beta, then we can also say that unbiased estimator ning beta hat na ato ang gi-define. Kini. Okay? In terms of mu hat or in terms of y pa, kana siya. So later, you will also see, aside from being unbiased, this is by definition of unbiasedness, aside from being unbiased, this beta hat actually is blue. So blue here, U here is unbiased estimate. BL will be the best linear unbiased estimate. So best linear unbiased estimate, the blue. Blue is a special case of the MVUE, or the minimum variance unbiased estimate. Minimum variance among all competing unbiased estimator, siya ang pinakagamay na variance. That is equivalent to being best, no? Best siya kay siya ang pinakagamay. Specific lang tayo ning linear because it applies because we can express it as a linear function of y, no, ang atong mga betas. So that's why it's called blue. And if this is normally distributed, so naman tayo equivalent na distribution sa mu hat, no? So ganitong distribution niya, mu, and then sigma I. Napot siya equivalent for beta. Tapos siya equivalent for beta, manapod siya equivalent sa imuhang sigma squared. Actually, the same ra siya, no? This is actually exercise B1 in the book, but I will not assign that as problem set anymore. You study for chapter 3 first. Okay, so this is non-central. Non-central, central chi-square. So let me end by this remark. So recall from lemma 2.2 that if V is in vector, your vector V is in V, if and only if you can express your vector V as x beta for xb for some vector B na p by 1. So if you look at this, kini imong V actually x beta, mo man ni ang mu hat, no? X beta hat. And this beta hat here is a p by 1. Also from theorem 2.5b, the square norm distance of y minus xp is always less than any competitive na parameter. So what is this saying? This is x beta b is the closest to y, no, that you can have. And this vector beta hat is called the ordinary least square estimator. So ordinary least estimator kining beta hat, no, nang ginatawag na to na least square estimator. So why is it least? Because what we are doing is we are trying to get the differences between y and our estimator ang pinakagamay, no, pinaka-least na square distances. So actually, we have derived this earlier na in particular, if we have a particular y here, you can express that in this manner. So this is similar to the earlier part here, kini siya. But what I used here is capital Y. Here, we will have a specific value Y. Or the derived Y. Okay? So usually when we have regression, natay intercept form katong y equal to beta. Kining beta null, di ba? Intercepts raman na siya, no? So simple linear regression. This is an intercept. So in general, pwede man ka walay intercept good. Y is equal to say just sum of the summation of beta I xi, no? So without the intercept. So but some regression usually ga-interpreta with intercept. Morning na ay 1-1 din to take care of the intercept. Okay, so we will continue on this next meeting, part lang, and then we will go with chapter 6. Actually, ano na naman ni siya? This is transforming the model when you have an intercept part. You can skip this part. Just read it. Central katura man ni siya when you try to introduce a delta, which is actually your beta null. Man kini siya will be beta 1, beta 2, and so on and so forth. You can skip this part and concentrate with the chapter 6, which is estimation. Okay, so unsa na gani atong schedule? Please